Let's take a look at the pH graphs when glutamic and lysine exist in solution with pH 1 and is gradually being added with sodium hydroxide. So when glutamic acid is in a solution with pH 1, the NH2 group will become NH3+, and hence this form of the amino acids will be tribasic, since 3 possible H+ could be released. And if we have to examine the groups and determine which group is the stronger acid, we'll be narrowing down to both the COOH group. And as a rule of thumb, remember that the carboxylic acid group nearer to the alpha carbon will end up to be the stronger acid. And it means that this will be termed as Ka1, which means that the Ka value is the highest. Following on to that will be the next carboxylic acid, which will be Ka2. And then finally, your NH3+ will be Ka3, which is the weakest acid of all. The reason why the carboxylic acid group that's bonded to the alpha carbon is a stronger acid is because after it dissociates its H+, the alpha NH3+, alpha means the alpha carbon. The alpha NH3+ is of close proximity to the COO- and it is an electron withdrawing group. As stated here, close proximity to alpha COO-. Thus, it helps to disperse and reduce the negative charge and stabilizing it. So that explains why this carboxylic acid group nearer to the alpha carbon is the stronger acid. So with that, let's take a look at the graph. So in the initial form for glutamic acid, as explained, there's 2 sets of COH, and this is actually the group with Ka1. This is Ka2, and this is Ka3. If you start off with 1 mole of this form of glutamic, after adding 1 mole of OH-, you will find that this is neutralized to form COO-. And in the second mole that is actually added, you will find that the next COOH is being neutralized to form COO-. And finally, when the third mole of OH- is added, all the NH3+ group will be converted to NH2. And in this case, there are going to be 3 buffer regions we're going to talk about. The first buffer region is here. And to be specific, you will find that at the maximum buffer cap, this value is actually pKa1. The pH is equal to pKa1. In the case of the second buffer region, the pH of the maximum buffer cap is pKa2. And finally, for the pH of the final buffer region, it will be pKa3. And from this value, we could also estimate. And from this value, we are able to estimate the pH of the equivalence point by, say, for example, the pH of the equivalence point, I'll add up pKa1 plus pKa2 divided by 2. And in this case, you can see that because the equivalence point is very near to pKa1 and pKa2, there isn't a steep increase. Unlike in the case of pKa2 and pKa3, where the average value is significantly different from pKa2 and pKa3, hence there's actually a steep change in pH during neutralization. Finally, it's important to identify where the pH of the isoelectric point is, which means in this case, you want the amino acids form to be neutral. In this case, you will be actually after adding 1 mole of OH-, and therefore the pH of the isoelectric point is pKa1 plus pKa2 divided by 2. Let's take a look at lysine now, in the medium where the pH is 1. So in this case, the NH3+ group, the NH2 will be converted to NH3+. And in deciding which is a stronger acid, it's clear-cut that carboxylic acid should be Ka1 because it's a stronger acid. And again, in the same vein, when you have 2 sets of NH3+ and you're not sure which is a stronger acid, the one that's nearer to the alpha carbon is the stronger acid. So this group will be Ka2, and finally, this group is Ka3. Let's take a look at the reason why. So the alpha COOH, which we know is electron withdrawing, is of close proximity to the nitrogen in alpha NH2. So that will render the lone pair electron of nitrogen less available for proton coordination. So in this case, I will know that I'm a weaker base, and hence because of that, my Kb2 value will be lower than Kb3. And since my Kb2 is lower than Kb3, I'm going to use the expression Ka-Kb equal to Kw. We are now able to conclude that Ka2 will be higher than Ka3. And therefore, because of that, this NH3+ that's bonded to the alpha carbon is the stronger acid. Let's take a look at now the pH graph. In the initial part of the pH graph, your lysine is actually tribasic as well, 3H+. And when 1 mole of OH- is being added at this form, your COOH is being neutralized to form CO minus. When another mole of OH minus is being added, the NH3 plus that's nearer to the alpha carbon is being neutralized since it is the next strongest acid. And finally, when the third mole of OH minus is added, you will find that the NH2 group, the final NH3 plus, is being neutralized to form NH2. In terms of buffer solution, the first maximum buffer cap is formed when pH is equal to pKa1. And in this case, your Ka1 is your carboxylic acid, being the stronger acids. In the pH of the second maximum buffer cap, you will be looking at pH equal to pKa2. For your final maximum buffer cap, your pH will be equal to pKa3. We also want to highlight at this point, if you were to calculate the pH of equivalence point, you will find that for the first equivalence point's pH will be pretty distinct compared to pKa1 and pKa2 because the value between pKa1 and pKa2 is dramatically different. However, in the case of the pH of the second equivalence point, the pH of the equivalence point is equal to half of the sum of pKa2 plus pKa3. Because pKa2 and pKa3 are of comparable values, you will find that the equivalence point does not have a steep change in pH, unlike in the case of your first equivalence point. Finally, it's important for us to identify where the isoelectric point is. The isoelectric point in this case is at the second equivalence point, because that is when the molecule is neutral, it does not have a charge. That occurs at the pH of the second equivalence point, which is actually half the pKa2 plus pKa3.